Well, it is value. It is config now, and make it simple.
Okay, so we don't need to worry about
Let's get started. So we talked about core optimization. It's been about 2 lectures on core optimization now, and I think we're finally ready to wrap up this discussion. And I released written assignment 3, I think last week, is that right? Thursday, and it's due about 1 week after you lab 2 is due, so that you have a little bit of window time to work on your written assignment 3, which is about core evaluation and core optimization. And moving forward, just to give you a heads up, we will have another lab, lab 4, which will be released right after you lab 3 is due, which is on core optimization. And then we will have one more homework once we are done with transaction. That's it. And I will be considering releasing another lab after lab 4, which is on transaction. But if time is a little bit too tight, I will skip that lab 5. But most likely, you will have 2 more labs and 1 more assignment. That's about it. And the final test is on December the 12th, I believe. It's in class, not in class, but around this time frame. And it will be open book. Okay, so you have access to lecture slide, written assignment, solution, and so on and so forth. So it's an open book test, and the test will basically covering things we have gone over in your written assignments. So the problem there will be similar to your written assignment problem. That being said, you really want to put in some effort in working on your written assignment, because essentially that's the type of problem you will expect from the final test. Now back to core optimization. Hello. Back to core optimization. So what we are trying to do is So we spent quite some time talking about a few things. Let me remind you, right? One is relational query-plan equivalence. That enable us to generate many multiple plans that are different, but different in the plan formation, but equivalent in query semantics. Okay? And then we talk about query selectivity estimation, which is important for you to estimate the size of your intermediate output, because the intermediate output will be the input for the next operator in your query plan tree. In order to estimate the cost of any plan, you need to estimate the cost of any operator in that plan. And in order to do that, you really need to understand the algorithm used for the operator as well as the input size. And for that reason, we need to estimate the size of intermediate output. And we have a very lengthy discussion on query selectivity estimation using a combination of different techniques, ranging from simple uniform assumption all the way to sophisticated histogram constructions. Okay? And then we talk about, okay, now you have query plan equivalence, you have selectivity estimation, you know the cost of different algorithms. You're almost there. The only thing to do is to enumerate all different equivalent plans. Because once given a plan, you should be able to estimate the cost using the machineries we have discussed so far. The observation though is that even if you go with left deep tree plan like illustrated in this slide, the plan space is still too big for you to afford to do a linear scan of all possible plans. So we need the last piece of puzzle, which is to find an algorithm that allow you to efficiently search through all these possible plans in the space of left deep tree plan. In the space of left deep tree plan. If you look at a left deep tree plan, in the very minimum, the possible plans, if you were to consider all possible plans in this space, in the minimum is equivalent to the size of the permutation of these tables. Right? Because I can basically permute these tables so that they are attached to different leaf level nodes, and each assignment basically give you a new left deep tree plan. And this is without even considering the fact that you may use different algorithms for different operators. And if you consider all these possible combinations, it's a huge combinatorial number. That basically shows you that the plan space is still huge. You still cannot afford to go through every one of them. So people propose this greedy algorithm. Towards the end of last lecture, I explained to you very briefly what's a greedy algorithm. One classic example of a greedy algorithm is gradient descent. That's heavily used in machine learning nowadays. You basically, suppose you are at the top of the mountain, at the summit of the mountain, you want to descend the mountain as quickly as you can. What do? While you look around, it all looks similar to your trees and paths and whatever. You don't know where to go, so you basically choose the slope that has the steepest angle going downwards. But that might not be the optimal solution. It's the optimal local choice you can make, but it may not be the optimal global choice you can make. However, typically that still works well in practice. And so the query optimization algorithm I'm going to introduce to you today, in principle, is exactly the same as gradient descent. In other words, tries to be as greedy as you can to choose always a local optimal, and then from this you slowly build up the curve plan tree. Okay, so that's 10,000 feet. If you look at this algorithm, what it does. Now let's get down to the ground and try to understand what exactly this algorithm does, and how the algorithm actually leverage this principle of greedy local optimal optimization that I have mentioned in constructing a search plan algorithm. So the algorithm proceeds in multiple rounds or multiple passes. And this is a distinct feature for most greedy algorithms. Most greedy algorithms, they proceed in what we call iteration or rounds. And in each iteration or round or pass, whatever you call it, they try to make some local optimal choice. before proceeding to the next round. And by doing so, because you are making some local optimal choice in each round, you cut the search space dramatically. The reason is you no longer need to consider the combinations of different choices you made in different rounds. Give you an example, right? Suppose this is point A, this is point B, this is point C. And there, let's say between A and B, I have 3 different paths to go from A to B. I have 3 different paths to go from Salt Lake City to Provo, let's say. And then from Provo to, I don't know, to St. George. Fantastic, I love St. George. If you have not been there, you should go. It's a nice place to visit. There is a university there as well, I think Southern Utah University. Anyway, let's say there are 4 different passes to go from Provo to St. George. In reality, there's literally just one, I-15. Right? But imagine there were 4. And how many combinations you can go from A to C? Well, it's very trivial, right? These many combinations. And if you continue this pattern to multiple levels, you end up with exponential number. That's the problem, right? The local optimal algorithm argues that I may not know the global optimal path. And to find that, it's very expensive. I need to search through all these combinations. So what I'm going to do is I'm going to make local choice from A to B. That's my path 1. I evaluate all the possible choices I have going from A to B. I make my best guess. You know what? I go with this. This is the shortest path. And then going from B to C, I may look at the shortest path and look at which one I'm going to choose. Then I just combine the 2. Of course, in the shortest path example, this actually is not necessarily a good example. Local optimal actually leads to global optimal because you simply add up the distance, right? So the shortest path from the first one plus the shortest path from the second path does give you the global shortest path. But this may not be true all the time, right? Your local optimal choice might not lead to the global optimal choice. However, this demonstrates to you, at least using this local optimal approach, you can cut down the search space dramatically. Your cost now become linear to the number of choices you have accumulated from all these different passes, rather than a combinatorial number from all the different choices you have to make in each round. Okay, so that's kind of the basic principle. Let's see how we do that in optimization. Keep in mind, we only consider left equal plan. So in pass 1, what do? Well, we find what we call the best one relation plan for each relation. The best one relation plan for each relation. What does this mean? Well, you have an input query, right? What you do is, given that input query, you figure out what are the query conditions concerning a particular relation. Let me see whether I have an example. So let's say that's my example right here. So the selection condition on both is color equal to red, right? What about reserve? Currently there are no condition on reserve, and there are no condition on scissors. So what do I mean by best one relation plan? Well, for both, I basically evaluate all my different choices and look at what's the best way to execute this selection condition on color over both. The most naive approach, obviously, is linear scan, heap file scan. However, if you know some additional information about your data, such as this information from your catalog, if you know there's a B+3 and a hash index on color, then you can answer this same query using either B+3 or hash. That makes sense? Okay? Using either B+3 or hash, or heap file scan. So you have 3 different choices just for answering this selection condition on both. What you do is, among these 3 different access methods over both, you select the best access method, meaning whichever gives you the smallest cost, you stick with that. You stick with that. And that's your best one relation plan for both. And you carry out the similar procedures to the other base relations. Base relations are those relations in the front clause in your input SQL operators. So far so good? So basically you evaluate each relation independently of the other relations, and you figure out what query conditions from your input query are related to one of the input relations. And then you consider what's the best you can do to answer that query condition for that relation. And that's what we call the best one relation plan. And this obviously is linear, right? Linear to the number of input relations you have, because you do this for each one of them. Okay? So that's for the both. What about for the reserve and sealer? For reserve and sealer, currently, you notice that there are no, even though there are no selection condition, but you do notice there is a join condition on that, right? There is a join condition, on reserve and sealers. You do notice there is a selection condition over there. So potentially, you might have to do a selection condition using both ID to probe the reserve and the sealers. Does that make sense? So potentially. But the tricky part is you don't know what particular set ID or both ID you need to use in order to probe the reserves and sealers yet, because that's dependent on what's coming out from the left-hand side of your join. You follow me? So you don't know what to do yet. So the best one relation plan still is just do simple cloud scan for those guys. Follow me? So far so good? Okay, cool. So you come up with, that's the result for you pass one. You understand how we come up with this result? You may wonder, wait, hold on a minute. I said, best one relation plan, right? So best means there's only one choice for each relation. Why? You are keeping both bstring and hash access methods for the color over both. Shouldn't be, in this case, you always use the hash index over color because you are doing a equality search. And hash index typically perform better on equality search over bstring index. So the best one relation plan shouldn't that be the hash index over color. Why you want to keep both of them? So this is another subtlety you need to pay attention to, which is in each pass, you keep the cheapest plan, the overall cheapest plan for this pass, for this relation. That's what we mean by best relation, the best one relation plan. But in addition, you also keep something called the interesting order. Those access methods that give you an interesting order in the output, even though they may not be the local optimal. But as long as they produce an interesting order in the output, you keep them. I actually had a discussion on this the other day when I talked about that hash join example, right? When I motivate why people still concerned about designing sort merge join when hash join is always better than sort merge join. I had an example of it, right? I motivate you. The reason is that the output of a sorting-based join algorithm is sorted, and it may facilitate the downstream evaluation of some query operators. In that particular example I give you, I show you if you do A join B join C, A join B then join C, that's three relations joined together. Yes, if you look at the local optimal plan for A join B, hash join is probably much better than sort merge join. However, if you do use sort merge join for A join B, the output is already sorted. And suppose they're sorted on the join attribute that will be used to joining with C, and then that A join B output join with C can be done much faster overall. If you look at the overall query cost, right? I did that calculation over there. If you forgot my calculation, you you can go back and search through that YouTube video and look at exactly the math I derive out for that particular example. That being said, that's a perfect example of what we call an interesting order. So if you just look at A join B, the local optimal is what? Is to use hash tree. That's the best local plan you should keep, which is this one. You keep the cheapest plan overall in this current phase. But in addition to that, not only you keep that, you also keep those ones do give you an interesting join order, an interesting order. Like sort merge join is a perfect example of that. It gives you a sorted order. But not necessarily, sorting is not necessarily always an interesting order. It's only interesting if the output is sorted on an attribute that later will be used by some of your other operators. For example, later on you have a group by on name attribute, and in the early stage you have a join over name between A and B. Then sort merge join for that is interesting because having the output sorted by name will facilitate and speed up the query answering for group by on name. But if later you only have a group by on age and you have a join of A join B on name, then in that particular example, sort merge join over name for A join B is not an interesting order anymore. It's not an interesting order anymore because it doesn't facilitate the answering of the group by query down for the downstream evaluation of your query operators. Okay, look at these two examples. That's what I'm trying to argue. When you are evaluating these two guys, these two relations joined together on name, the optimal local plan for this most likely will be hash join. Most likely, right? If they satisfy that condition, which condition? The m over b must greater than the square root of minimum of n1 over b or this, then you can do this in linear I/O. Right? This is the condition we argued many times. So hash join most likely will be the most efficient plan for the join operator. However, for this one, an interesting order is sort merge join on name. Why? Because if you use this, the local cost might be higher than using a hash join approach, but the output is sorted by name, so that you can immediately perform the group by because it's sorted by name. Whereas if you use hash join as a local algorithm, which is optimal, locally speaking, but once you come out of the join, you try to do the grouping, you still need to do another hash for sorting on the name attribute in order to do the group by. Right, in order to do the group by. In particular, in this example, the output is already hashed by name, by the way, if you're using a hash join. So it can also facilitate the group by. However, keep in mind, if you compare performing group by using sorting and performing group by using hashing, if the input is already sorted, the sorting approach is guaranteed to be always more efficient than the sorting than the hashing approach. Why? Because hashing may potentially have clears. But sorting guaranteed, the records are already properly grouped together, guaranteed. So sorting is an interesting order in that case. Whereas if you consider the second example, you will only keep hash join as a local optimal plan. You will not even consider keeping sort merge join as an interesting order. Why? Because sort by name doesn't really help you at all with the grouping of age. It doesn't help you at all. You may argue, wait a minute, maybe using sort mergeon plus grouping by age is more efficient than using hashron plus grouping by age. Yes, potentially that might be the case. But go back to exactly this argument, we just cannot afford to consider all these combinations in order to find the optimal global plan. So what do? We consider only the local optimal by using a greedy approach and build up the plans step by step. Okay, so that's the idea. Now, once you understand that basic idea, let's look at pass 2 and pass 3 and so on and so forth. So in each pass, we find the local optimal argument for all possible combinations of relation in that pass, plus all the interesting orders. So in pass 1, it's really just to find the best one relation plan, as well as those interesting order one relation plan. For that reason, in this example, we will be considering both the hash index as well as the B plus 3. Why? Because B plus 3 might be a cluster index on color, so that output of color is sorted. So it could be useful for the downstream pre-evaluation. Actually, in this case, in this particular example, cluster index on color doesn't really help you. What you really need is maybe an unclassed index on color. However, the records in that B plus 3 are sorted by boat ID. Then using that B plus 3 to retrieve those boat records is still very useful for you because output is sorted by boat ID. That will facilitate the answer of this drawing query, potentially. That's why it's considered as an interesting order. So only if the boat records are sorted by boat ID and you can use the B plus 3 on color to retrieve them, then that's an interesting order. What about pass number 2? Now you have all the pass 1 output, which is the best one relation plan plus those interesting order plans for one relation. What do you do in pass 2? Well, find the best way to join results of each one relation plan as order to another relation. This is important. You take the output from the best one relation plan and always treat them as the outer relation, and you try to join with the other relation that this relation can join with. In other words, these are your best one relation plan, right? Plus interesting orders. What you do is in pass 2 is you consider all these combinations. Give you a few seconds to look at these combinations to understand what it does. Okay? So for example, this is the best one relation plan for reserve, right? You use that best one relation as order. You try to join this with boat and with sitter. In this case, you can try both because reserve can join with both boats and sitters. Right? It can, right? Join on boat ID and on sitter ID, respectively. So basically, for every other relation that you can potentially join with, of course, without violating the relational equivalence to your ordinal query plan, you try to join them together. But always keep the best one relation as outer. What's the rationale we keep the best one relation plan as outer? Because we want to make sure it's a local greedy approach, right? So we keep that as outer, meaning that we're going to evaluate that first before we perform the drawing, so that it is actually following a greedy approach. Similarly, for the sitters, the best one relation plan is file scan over sitters, so you try all the combination with both and with them. And lastly, boat is a little bit complex, right? Because it has two plans. One is the best one relation plan over both, which is hash. The other is the interesting order of both, which is B plus 3. So you have to try 4 possible combinations right here. But you always keep those from the level 1, from class 1 have altered. Do you follow me so far? Yes or no? So far so good? Okay, cool. For each such combination, this is critical, okay? This part is critical. For each such combination, you keep the best plan. And that's what we call the best two relation plans. That's called the best two relation plans. For each pair of relation, this is important, right? So for example, if you look at boat and sailor as a pair, if you look at boat and sailor as a pair, boats. How many plans we have here in this space? We have this one right here, right? We also have all these two ones, these two guys. So altogether for this pair, you have 3 plans. What do? You keep the best one for this pair. When I say a pair is unordered, so both and sailor is the same as sailor and both. Doesn't matter which one is ordered, which one is linear. So if you look at what you get after pass 2, what do you get? For any possible combinations of pairs of relation, you find the best local plan for it. Again, it's a greedy algorithm, right? It's a greedy algorithm. Yes or no? In addition, for each such pair, in addition to keep the best plan for that pair, you also keep whatever interesting other plan that you may encounter. One potential misunderstanding that people may have about this algorithm is it's a greedy algorithm, but it's not a really aggressive greedy algorithm. Why I say that? Because if it's a really aggressive greedy algorithm, what you would be doing is to consider all these pairs, then keep only one best plan for all possible pairs. That would be the really aggressive greedy algorithm. But in practice, why people don't do that? That cut on your search space dramatically compared to this, right? Because if you consider this approach, potentially it's still, the search space is still potentially big. Because you're looking at all possible pairs of relations, that's already potentially n squared for n relations. Of course, in practice, it's not going to be n squared. Why? Because not all relations in your input join will be able to join together. Like student join with reserve, join with class. 3 relations, but it doesn't really give you n squared combination. Why? Because student and class don't even join. Do you follow me? But potentially, worst case, you can construct a case where every 2 relations can join together. Then it is n squared. Even after you do this left deep plan, even you do all this, even you use local greedy approach, using this algorithm, because you consider all the combinations between pairs, you may still end up with an n squared search space, even in level 2. In level 3, it's n cube and so on and so forth. However, 2 observations people have made. One is typically n is small. For most database queries, n is 2 or 3, and most 6 or 7 tables. Plus, not all the relations are joined. Like the example I gave you, student join with reserve join with class. It doesn't really give you the worst case scenario. Student doesn't join with class. You don't have to consider that. So we can really afford to do this. The reason we do not use a really aggressive greedy approach, meaning keep the best plan for any pairs, rather than for each pair keep the best one plan. These are 2 different things. The reason for that is too greedy. And you may end up in things like this. If you're trying to be too greedy, you say, okay, I'm here, I should jump here. But let's say this is the Pacific Ocean, and your goal is to reach ocean from the top of mountain. This is the Pacific Ocean. And somewhere in California, you say, I do this. I go this way. What you end up is you have to cross the entire United States to reach, what's the other ocean? Atlantic Ocean. You're trying to be too greedy. You follow me? That's why people don't simply keep the best plan for any pair. Rather, for any pair, I keep the best plan. These are two subtle, different concepts. Okay. I think I can stop right here, right? Because once you understand this, what do? You move on to keep those for all such pair. You keep the best best two relation plan for each possible pair, plus interesting orders. Then you move on to the path number 3. For each such best two relation plan, you try to join the remaining relations. Of course, using this again as order. Then for every triple of such relations, regardless of order, you keep the best 3 relations plus interesting orders. I think I can stop right here. It's the remaining part is just the repeating of what I have just said for the previous parts. It's basically the same. You repeat the same step over and over again, using this local greedy algorithm to proceed until you reach what? The best n relation plan. Of course, quote unquote best n relation plan, because it is not always going to be the best optimal global n relation plan. It's just constructed from this greedy approach. So quote unquote best n relation. Alright, so that's it. Yeah. Okay, we're done with this Q optimization algorithm. Okay? Alright, I think it's fairly sounds complicated. Q optimizer. Now I want to pause a little bit, like recap what we have been seeing for Q optimization. Right? Q optimization is indeed a very deep topic, very difficult topic to understand. But once you take the approach we have been using, which is you break this complex piece into small sub-modules, you understand each part. Now if you allow me to go all the way back, to this. Now you should have a crystal clear understanding of each of these components. Plan generation use relational plan equivalence. Plan cost estimator use catalog manager that maintain information about your schema and some statistics about your relations, such as histograms. To do what? To do 2 things. To do selectivity estimation, as well as using the analysis of different algorithms we have been talking about, estimate the cost of each operator, whether it's hashed one or merged one, or nested loop, or block nested loop, or whatever. And then it's a feedback loop. Given me a plan, what I will do is I estimate the cost of each operator bottom up. While I do that, I estimate the output size using my selectivity estimation. And then the output size becomes the input size for the next operator in the tree. I do that. And then inside this box, I use 2 things. One is relational plan equivalence. One is what? The plan search space algorithm we just talked about, using the local greedy algorithm. And every time I will output one. Essentially, what the plan generator will do is basically, given an input plan, generate all these possible left-free plans using this greedy algorithm approach. Best 1 relation plan, best 2 relation plan, all the way to construct best n relation plan. At the end of the day, you may have several plans. At the end of that best n relation exploration, you return each one of them to the plan cost estimator, estimate the cost. At the end of the day, you choose whichever has the smallest cost. Now you should be crystal clear to you guys, right? Now, one thing to note is that this does not guarantee to find the optimal plan. It does not. What it does give you is a reliable algorithm or procedure to get rid of really expensive plans. Using our running examples, what this one does is to get rid of a plan like this guy, this guy, and this guy. And this 6,000, maybe I will keep it. I don't know. So I will give you these plans as your possible choice. I may not be able to all the way to find like this plan, like only like 1,000, 2,000 hours. That really take something as smart as a human brain to do it. Because this problem is NP-hard. Okay? The final note I want to mention is the landscape of co-optimization is slowly changing nowadays. If you look at what we are doing is we're using a really traditional classic computer science approach. We combine technique from statistics and algorithm analysis combined together with derived a co-optimizer as we have presented to you. Slowly in recent years, people have picked up sophisticated machine learning algorithms, such as deep learning, to try to integrate that into co-optimization. The idea is, if I have a vast collection of past query workloads, and I know what each query cost is, given the data workload and the query workload, and I learn some features about the data about the query, right? If I say, okay, if it's a 3-level join with index on this table, that table, from 80% of my workload, this query plan is typically the best. So I learned some features from that using a learning-based approach, such as deep learning and things like that. Then I can build a classifier, and this classifier can quickly tell you, it may not be able to tell you the optimal plan, but it can quickly tell you a promising direction to search for optimal plan. That might help you reduce the search space dramatically before you embark on an expensive but more fine-tuned co-optimization only in that subspace. Does that make sense? Yes or no? For example, using election example, right? I want to know where I can find a lot of support for Hillary Clinton. This is a hard problem to start with, but using past election data, I can tell you, well, I don't know where you can find a large number of Hillary Clinton supporters, but you don't want to start with Texas. Right? You may be, you want to increase your chance of success. I really cannot tell you where you're going to find the most number of Hillary Clinton supporters, but you cannot go wrong by starting with California or Massachusetts or New York. Then you spend all your money and energy searching for the area with largest number of Hillary Clinton supporters from only California and New York. Now you can afford to do that. You cannot afford to do that over the entire United States, but you can afford to do that in a zoom-in area. That's kind of the idea people are using nowadays, right? Using machine learning technique to quickly rule out things like Texas and so on and so forth. Does that make sense? Rather than embark on an expensive search of which area has the largest number of Hillary Clinton support over the entire United States. Yeah? So that's kind of an active area of research nowadays. It's very hot, and it's not easy, actually. But I can roughly tell you some of the activity in this space. Lastly, the last point to take away is, what about nested queries? Well, I talked about this at the beginning of last lecture, right? So for nested query really is the enemy of co-optimizer, because co-optimizer, as it is now in most commercial database engines, is simply not able to optimize sophisticated nested queries, because the correlation and all that has just become too complex for a co-optimizer to reason about. So what they end up doing is to, like I said in the beginning of the query optimizer discussion, is to optimize each block independently. And that's why, that being said, whenever possible, when you are managing a large database for whatever company, try not to write nested queries. Especially those nested queries with correlations. A lot of optimizers nowadays can do a good job of optimizing nested queries when the blocks are not correlated. but they are not able to do a good job when the blocks are correlated.
By correlated, do you just mean that the inner query depends on the value inside the outer query?
Totally. I mean, refresh, you guys memory on.
I apologize if you discussed that last
No, it's
week.
fine.
I was
Totally fine.
gone.
No, totally fine. So I encourage questions anytime, okay? So don't be shy to ask any questions. So this is an example where, but you are actually absolutely right. A correlated block is an inner block is a case where the inner block has a query condition depends on the current value for the current record from the outer block iterations. And this value will actually change from iteration to iteration if you view or understand nested query as a for loop, nested for loop kind of semantic. So this is an example where it is correlated because the inner block has a query condition depends on the value of the current CLID from the outer relation, which change when you go from iteration to iteration. This is an example where it is not correlated. Because no matter, right? Because for each differentiator from the outer relation, the inner block is a constant. And two-element analysis can do a fairly good job for this uncorrelated nested blocks. But still, it's a long way to go from there to correlated blocks. I mean, intuitively speaking, it's just like when you do analysis in data science or statistical analysis, independent random variables are always much easier to work with than correlated random variables. Right? That's why people spend so much time designing universal hash family functions because they give you pairwise independence or three-wise independence or whatever after hashing. All right. Okay, let's start with something. I'm going to switch gear. And we're going to go to the last pass, the last component of this course, right? Transactions. So far, okay, look at what we have done, right? We have learned a lot, right? So yeah.
Sorry, one more question.
Yeah, go ahead.
Is it always, I mean, given a correlated nested query,
Yes.
is it always possible to rewrite that into a non-nested query?
Excellent question. Excellent question. So let me repeat the question, right? Given a correlated nested, is it always possible to rewrite that into a query without nested blocks? The answer is no. In some cases, you can rewrite that into a join. In some cases, you can. But in some other cases, this is not possible. Actually, the way you can argue for this is to use a counter-argument. Right? If this is indeed possible, there's really no need to introduce nesting in the first place. Because clearly, the uncorrelated nested queries can be expressed using join. That's fine. Right? So there must be a reason why people did not nested query in the first place. All right, so let's move on to the last piece of the puzzle in a database kernel. Even though this is the last piece, but actually it is the, in my opinion, most important piece of the puzzle. More important than optimization, query validation, and all these things. Why? The reason I said this is, I give you two cars. Allow you to choose one. One car is fantastic, like a BMW, Mercedes-Benz, really luxury car, drive really fast. Everything is perfect. You look at the interior or exterior, it's like my dream car. Fast, efficient, scalable, everything. And the other car looks like really clunky car, cash for clunk, right? That was done in Bush administration, right? Like a really clunky car. Everything you will not hope for is in that car. Right? It seems like the choice is clear, right? However, just before you sign the deal with the salesman, of course, price, you will say, oh, obviously the first car is more expensive. You know what's the surprise? The two car price is the same. Surprise. So you're like, oh my gosh, let me sign this deal before it's gone. Just before you sign the deal, the sneaky salesman said, really low watts. Just so you know, there is 50% probability that the first car may drop a wheel when you drive it on a highway. And you ask, what about the second car? Well, 100% guaranteed, will never come out. Which one will you buy? Which one will you buy? Well,
go to a different salesman.
but it's a make-up story, right? But it has a fundamental principle I'm trying to argue for, which is efficiency, scalability. All these are fantastic things to shoot for. That's what we've been doing, right? All the index, all the hashing, all the algorithm, all the optimization. We spend so much effort, but they only serve their purposes if they deliver the correct results at the end of the day. If a database engine doesn't give you correct results, I would not be using that, no matter how efficient it is. So where database is used? Well, database is used by banks. It's used by Amazon.com to track your sales orders. If you go tell Amazon.com, oh, I'm gonna sell you this fantastic new database engine that's 10 times, 100 times faster than what you're doing now. You can speed up your productivity, your number of sales 100 times. Amazon is like, oh, fantastic, and the same price as whatever product you're using now. But keep in mind, from time to time, it will mess up your order. Like you're supposed to sell this to somebody. If they bought a computer on Amazon.com, the order quantity is 1, but potentially I may mess up that to 100. You have to deliver 100 computers to this guy. And the other person comes in like, I did it slow and all that fine, but you know what? Whatever he described would never happen in my database. So Amazon will go with the second guy for sure. And banks too, right? Does that make sense? If it's my salary database, I may go with the first one. Oh, there's a potential 100 times. You know what? Take that. But it goes both ways. It may reduce this error 100 times. But if my salary is so low, I better take the risk. Seriously, if you're Bill Gates, you probably say, no, thanks, I'm not going to take it. But it's like you're like one of us, like us. You know what? Take the risk. No? Right? So I use these examples to motivate the discussion of transaction is designed for this purpose. So far, we talk about database under the scenario of only one user using the database. Only one user using the database. And plus, most of the discussion, except at the very beginning of the course, we talk about insertion, deletion, and update a little bit. In the remaining part of the lecture so far, we talk about, you have a bunch of tables, you have queries, even the computation we're running right now is all about how to get the results fast. But what about if you are executing your query while somebody else is accessing the database and making some changes to the database? Like you go to Amazon.com, you try to order whatever item, really good deal. You try to make an order. If you don't design your database carefully, you may end up in a scenario where Amazon is over-committed. You only have 100 such items to start with, but because it's such a good deal, thousands of people come to watch and order for it. And you accept all the sales orders, and you end up committed to sell more than what you have. What do you do? And to cater for this is what we call transactions. And people in database community, they design this concept called transactions to insulate attacks or potential threats to the underlying database using this mechanism called transactions. What I have motivated you so far is really on the first bullet point here, which is concurrent database access. But in addition to concurrent database access, another point I try to make is, what if system fails in the middle of your access to the database? Like you execute a bunch of really expensive and important operations to the database, but suddenly the database loses power, the machine running the database server loses power, or hard disk goes bad or something like that. How do you make sure you can restore the data properly? how do you ensure the data can be restored properly without the worry about losing all your data? Right? So really, these two reasons are the driving force behind the design of transactions. So here is a simple scenario setup. We have an EDMS running over your data. And the data is stored in a database. It's catalog, heap file, all that stuff, necessary structures, all that stuff. Okay? And you have software on top using your database. Right? Like the GrabTrack system we've been using, that's a software running on top of the database system. Okay? And you have even more software. For example, your mobile phone nowadays can connect to database, some application running at the back end. Many users talking to the database at the same time. And they do this different kind of query things over the database. Like somebody is executing a selection query, somebody is doing an update, somebody is creating tables, and so on and so forth. I'll give you a simple example, which is this one. Let's say I want to build an enrollment database for Stanford. And I say my enrollment number I want to grow by 1,000. That's one administrator. Let's say we have 2 college administrators for Stanford. I want to do this. And one says I want to increase by 1,000 enrollment number. The other says I want to increase by 1,500. What the final value should be? Well, the final value should be, if the initial value is x, the final value should be x plus 2,500. But in reality, if you do not have comparison control, what will happen? What will happen? Well, I will show you. I will use the whiteboard to illustrate this point further. This goes back to an old school concept called semaphore. Have you guys heard of semaphore? So what's semaphore? What's semaphore? I don't know what semaphore is. While we are in 24th century, Google it. Okay, so that's exactly what I'm going to do. So these are semaphores. Semaphores are control signal used by, in the old days, used by the train system. Like these are semaphores. Green, yellow, or whatever, right? Different combinations. Like whether you go or stop or slow down, whatever. That's called semaphore. So why semaphore has to do with database? Why train somehow has anything to do with database? Well, it has, you will be surprised, they share a lot of similarities. So suppose you are given the following task, like Natural Museum of History, right? Natural History Museum, they ask you to implement a very simple program for them, and they are willing to pay you like $1,000 for it. And all they are going to need to do is to keep a counter on how many head count currently in the museum, how many visitors in the museum at any moment in time. And they give you the necessary hardware. Suppose the museum has 2 doors. Suppose I have 2 doors, and one is for enter, one is for exit the museum. So everyone going through this museum must enter from here, must exit from there. And furthermore, I make your job really simple. I give you sensors here, and some sensors here, that whenever a person passing by, the sensor will send a signal to your code. And you will be able to tell whether the signal coming from here or here. So you say, oh, this is the $1,000 I can make, right? So what you do, you say, you go through, you wait for signals, it is plus signal, what I do? I initialize my counter equal to 0, my counter equal to counter plus 1. That's it. And this, you run this at thread 1, you use P thread, and you spawn 2 threads. One does this, the other one does exactly the same thing, but if it's minus signal, my counter equal to counter and minus 1. Of course, they share, the counter value is initialized before you initialize the 2 threads. So they share the same variable. Alright? You return this code to museum and say, give me the sandbox. That's easy money to make. What's wrong with this code, by the way? What's wrong with this code? If you run this code, in most cases it's fine. That people enter E plus 1, people exit E minus 1. How can this go wrong? How can this be wrong? How can this be wrong? And this must be right. However, this actually is not going to work. The reason is, give you a particular scenario. Let's say the counter value now is 99. At some point, at some stage of your code, running your code, counter becomes 99. There are 99 people currently in the museum. And somebody tries to enter from here, and somebody tries to exit. What will happen is, so let's say this happened first. Okay, I enter first. What would you do? To execute this code, what do? You have to read the value of counter from main memory and bring that to the cache. So this is your memory, counter equal to 99. So what you do is this, I call this T1, this is T2, thread 1, thread 2. What will happen is thread 1 will go and fetch this to our 2 cache, to your CPU's data cache. So it's 99, and you execute this instruction from an instructor, from the instruction instructor. So there is instruction register. Anyway, the instruction register. Okay. Right. There is that addition instruction you're going to execute over this code, over this value, right? That's how computer works, right? If you have taken a computer architecture class, you know exactly what I'm talking about, right? Cache is just register, you have data cache and the instruction cache. You store all the instruction to be executed by your code into the instruction registers. You store all your data or parameter needed for instruction in the data cache. Then you just using assembly language, using the particular architecture you're using, x86, whatever, to execute the instruction over those data, right, in data cache. So you 99, then you execute this. This becomes what? This becomes. But at the same time, remember that thread T2 will come in and try to access this as well. So what it does is there's instruction 1 and instruction 2. And instruction 1's knowledge is 99, instruction 2's knowledge is 99 as well. So what this guy will do is, I will say, I will write 100 back, but this person will write back what? Minus 1, right? After you execute that instruction, well, this value will become 98. And then this is written back. That obviously is wrong. The correct value should be 99. Of course, the reverse can happen, which is 98 is written back first and 100 comes back later. So this becomes 100. Of course, in another possible scenario is I will instruction 2 only try to access the data cache after instruction 1 has been executed. So it will become, from 99 it will become 100. And then you load 100 to here, then you write 99. Then in that case, that's fine. Or instruction 2 access the data cache only after instruction 1 has executed, or the other way around. In those cases, that's fine. But if not, you're in trouble. You code it wrong. Okay? And why this has to do with semaphore? The idea of semaphore is if you have to build a train station to cater for maximum 10 trains coming to that station, a really naive solution is to what? Is to build 10 tracks. Well, in the worst case, 10 trains come, fine. One go to track 1 to 10. But if you try to do that in a small town like Salt Lake City, I guess it's okay. If you try to do that over New York, the maximum is maybe 1,000 trains come at some time. You're going to build 1,000 tracks in Manhattan? Seriously? No way, right? Because you are wasting your maximum capacity. Maybe once in a year you have 1,000 trains come around the same time. You're going to use that on 1,000 tracks. Most other cases you don't. So what do people do? While you wait, you let the train wait. Suppose you only have one track, you have 2 trains trying to come. Well, one train go first, and the other train just wait until the other train completely done, then the second train can come. That's the idea of semaphore, right? Same thing here. If this is what you're trying to do, you use a semaphore to guard against this variable so that this operation becomes what we call atomic. Why call atomic? You know? Why this is called atomic? This is related with something called atom, right? What's an atom? What's a molecule? We're all molecules. I'm just billions of molecules standing out here. Seriously. And then billions more atoms here, standing here right in front of me. And people used to believe, physics in the early 20th century used to believe atom is the smallest particle that exists in universe. You can no longer divide atom. Like, there's nothing inside atom. Atom is like the smallest particle that exists in the entire universe. Of course, nowadays we know that's not true. Right? I hope you know that. Atom is not the smallest particle in the universe. There's stuff inside atom too. And it's fascinating. You Google this basic particle in the universe. There are tons of stuff. That's why they built this huge circular kind of machine in Europe, near Switzerland, to accelerate. Why they build a circular shape? Well, because they use a really huge magnetic field in the center and accelerate the particles surrounding that magnetic center. You go many, many rounds until it's accelerated to a really, really high speed, almost near the speed of light. You have 2 tubes. One particle goes this way, one particle goes this way. When they're close to the speed of light, you let go of the semaphore, so they collide to the same track, so they hit each other in high speed. Why in high speed? High speed means high energy. That's what Einstein told us. E equal to mc squared, right? So high speed gives you high energy. When they collide, hopefully that energy is large enough. So how do you break up a human body? You cannot break up a human body like this. You have to break up a human body using big force. Right? So when you have high energy, you break up that particle, and hopefully you can observe what's inside the particle. That's what they do, right? So the reason I mention all of this is to explain to why this is called atom. Because people used to believe atom is like, you cannot divide this anymore. Now you understand why this is called atomic operation, because this whole thing is not breakable, not dividable, not separable. So that if some other process try to raise or update the value of counter, it will be blocked until I'm done with my addition operation. That being said, now let's come back. Once we're using semaphore, let's come back to see this example. What will happen now is that you have 99 here. When this instruction go and access this to fetch 99 to feed the instruction is guarded by a semaphore. So this becomes atomic. So the second instruction, when you try to access 99, it will be blocked until I'm done with my addition operation and write it back, which is 100. Now my semaphore turns to green. You can go ahead and fetch 100 minus 1, you got 99. So everything works just fine. Everything works just fine. Do you follow me? So in this example, if we don't use something similar to semaphore, database is going to suffer from exactly the same problem. You may end up with a value that's x plus 1,000 or x plus 1,500 or x plus 2,500. Only in the last case you do get the correct answer. In the other two cases, the answers are wrong. Similarly, you can also have, this is an attribute level inconsistency because the inconsistency happens for the enrollment attribute. You may also have tuple level inconsistency in a database engine. I'll give you this example. If you try to update apply database, apply is let's say all the students applying to University of Utah. And in particular, people are trying to get into CS major. And each record has multiple attributes, right? So there's an attribute called major, there's an attribute called decision. But it's in one tuple. One tuple. What I'm going to do is, this major for this student is not decided yet. He or she may apply to do many different majors. Finally, one administrator review his or her file said, this is a good student for CS. I want to admit him or her into CS. So I will be executing this particular state, right? At the same time, but let's say the default decision for admission is no. Default decision is no. The default value for decision is no. By default, you don't admit anyone. You only admit those with yes. And the default major value is none. There are no major. Okay? Let's assume that's the case. So you start with this record with no for decision value and none for major value. Now this guy comes in and says, I'm going to set the major to CS. Another person at the same time fetch this record and say, I want to update the decision to yes. What will happen at the end of the day when you're concurrently executing these two statements? Well, you may end up with one of the following. One is the major becomes yes, admission decision is no. Or major is no, decision is yes. In either case, it's not right. Right? What's the correct answer? The correct answer is major is yes and decision is yes. That only happens if you execute the two in sequential order. Another really important, and later on we're going to leverage on this operation, is it only really matters if you execute these two statements in sequential order. It doesn't matter which goes first at the end of the day. Either you do this first or do this first. At the end of the day, as long as you execute two of them sequentially, one after another, not concurrently, you end up with the correct record you are hoping for, which is major equals yes, decision equals yes. You understand what I'm saying? So executing them sequentially is the key. Executing them in any particular order in this scenario doesn't really matter, as long as they are sequential. Do you follow me? Okay, this is a critical observation we're going to leverage on later on. Now, you may also have table level inconsistency. This is the worst case scenario. Okay? Table level inconsistency. Let's say we're doing this. What I'm going to do is I will say, okay, the first statement is for all students whose GPA is greater than 3.9, I'm going to apply them immediately. They're good students. Well, as the other one, I say, okay, for a particular high school, when this high school has a really large size of students, their GPA may bear a little bit more weight than a student from a high school with only 100 students. It's more competitive, right, when you have a large number of students. So what I will do, I will inflate that GPA for all the students from a high school with more than 2,500 students a little bit. I give them 10% bonus points. If you try to execute both at the same time, what will happen? Both statements affect the bulk of records, right? And if you try to execute them in concurrency, you can imagine things could go terribly wrong, obviously. Right? Some students that should be admitted, after applying this bonus points, will not be admitted because you executed them concurrently. because their GPA is still lower than 3.9, and they haven't got a 10% boost yet while you apply the decision for admission. And then there are also multi-statement inconsistency. And this is an example I will ask you to go and review yourself. It's very easy to understand. So the basic idea is to, from this mode running example, what you want to guarantee is to execute a sequence of SQL statements so that they appear to be running in isolation. What does it mean, isolation? Isolation means that even if database has multiple users having concurrent access to database, you want to design an environment where every single user only needs to worry about what his or her intent is. What I try to do with the database. I don't have to worry about the fact that there are other users concurrently executing the database. This is what we call isolation. I'm going to demonstrate this concept using a toy example. So this one I connect to our DVD rental database using the class-wide user account, CS 6530 user. And then the other one I connect to the database using the super user, Postgres. So the super user has full access right to this database, right? So I can read and write and so on and so forth. Okay? So what I will do is, first of all, let's show you the tables. They are connected to the same database, so not surprisingly, they see the same set of tables. Now, if I do a query here, there are 201 users found actually from the actual database. Let's see, I'm gonna see all of them. There's a 51 user here, actually. So if I do the same thing here, it's the same, right? Not surprisingly. Just verify really quick. Not surprised. They're connected to the same database. Now, if I try to delete that user, what's the name of this here? It's called XRD. This is a CS user, of course. I don't have information. I'm going to try to delete it here. Okay. Now, if you execute this, you got 200. If you execute this, you got 200. Perfect. Now, what I want to do is here, I want to start a transaction. So, the super user, Postgres, now starts the transaction. What I will do is I will insert into actor with values That's only two values I need to specify. It will automatically assign actor ID and update the update tab. Can you go back? Okay, so the transaction, let me start again. I think I have to specify the okay. Now what I will do is something weird is happening. Let me try one more time. If not, I will do this next time. I'll figure out what's going on. Okay, let me do a division. Okay, let me try to insert it one more time. If it fails, I will stop the class right there. I will continue next time. Figure out what's going on. Okay, I have to stop right here. Some configuration problem. But what I was trying to demonstrate is, once you use transaction to execute SQL statements, you get isolation. What happened to one user is not viewable to another user until the first transaction is committed. That was what I tried to demonstrate. Obviously, there's something happening on the database. So I see you on Thursday.
这个就是我给前面做，你给后面做。好。